In software engineering, we are discussing chapter number 30, Product Matrix. Architectural Design Matrix. So, we want to find out some numbers, some quantitative measure, so that we can understand what is the present state of architecture or the design. So, Architectural Design Matrix, they focuses on characteristics of the program architecture, emphasizing on architectural structures and effectiveness of modules or components. You know that the architecture is what? The overall structure of the software. And design is that total conversion of requirement so that it can be converted to the actual code. So now these things need some numbers, whether we have made a good architectural design or not. So these metrics which we are going to discuss, they are black box. We don't go into the detail or we don't have any knowledge of the inner working. Card and Glass, they define 3 software design complexity measures. What are these measures? These are pertaining to your architectural design. So the first one is structural complexity, then the data complexity, and the system complexity. Complexity, we have already talked about cyclomatic complexity. So this kind of complexity or this kind of measures or metrics can also be talked about in here. So here we have a call and return architecture. That is, the main module or main function will going to call certain function. Those functions are going to call again some functions. So these are a kind of call and return architecture. This is a hierarchical architecture. We have a proper hierarchy here. Okay. Now for this hierarchical structure, if we want to define these different complexities with respect to the architectural design matrix, the structural complexity of a module I, module can be a combination of functions. So this is defined as what? It's simply the square of fan out. For that module or that group of function or a separate function, just square the fan out. Now the question will be, what is the fan out? See, the fan out is the number of submodules this is going to invoke. For example, here there is a component. Now here we have different functions calling this component or this function. This is called fan in. That is, fan in is this function is invoked by others. But fan out is how many components or the modules or the function this component is going to invoke. Okay. So usually we want high fan in and low fan out. We don't want low fan in and high fan out. So fan out is that a module or a component, how many it is going to invoke. So this is the fan out. So just square it, you are going to get the structural complexity. Now coming to the data complexity. The data complexity is the complexity in the internal interface for a module I. How do we define it? What is the interface? How do you get inside a function or a module? Through variables. And what do you get from these functions or the modules? Variables. So we are talking about the number of input and output variables that are passed to and from this module. Vi divided by fan out plus 1. Fan out we know, number of modules or functions this module is going to invoke. But Vi or V is the number of input and output. For example, let me make a function. Assume that it takes 4 variables as input and it is returning, or say through pointer or by any other mean, it is returning say 2 variables. So number of Vi is the number of input and output variables. So in all we have 6. So that is what you are going to put it here. Fan out is number of modules this module is going to invoke. Coming to system complexity, in the architectural design matrix, just add the structural complexity with the data complexity. This is the system complexity, because we already talked about the fan out and input output. So all these complexity, the question is, the word complex is complex. So the complexity value, if it increases, the overall architecture complexity will increase, and thereby the effort in integration and testing of these modules will increase. Now Fenton, he suggested a variety of simple morphology that is based on the shape. Morph is shape or face. So simple morphology matrix in order to compare various program architecture and using very straightforward dimensions. What are these dimensions? If we take call and return architecture, that is a main function calling a function, then that function is calling another function, likewise. So call and return architecture, if we take, the simple straightforward dimension is when you make this graph or this figure, the simple way to find out the size will be n plus a. What is n here? N are these blocks, which are the number of nodes in this graph, and a is the number of arcs. These are the number of arcs. So n plus a, nodes plus arc, is going to give you size. So when you add them, if you consider these nodes, there are 17 nodes. How many arcs are there? There are 18 arcs. Add them, and what are you going to get? 35. The size you got. There are other parameters also, like the depth and the width. So depth is the longest path from the root, which is the top node, to a leaf node. So in the figure, if you see what is the depth, you can just see how many levels it has. 1, 2, 3, 4. So depth is the number of levels you can assume. So this is the longest path from the root to the leaf. So the answer here is 4. Depth is going to be 4. What about the width? Depth is from top to bottom. That is how we got 4, the depth. And the width. Width is the maximum number of nodes at any one level of architecture. That is, we have 4 levels, which is of course our depth also. And width is what? The maximum number of nodes at any level of architecture. So you just compute this highest number of these boxes, in which level they are. In the second there are 6. In the last one also we have 6. So width is 6. So arc to node ratio, arc can be computed as A divided by n, number of arcs divided by number of nodes. What do you get? You have the numbers. So this value will give you the idea about the coupling of the architecture. So this R equals A by N measures the connectivity density of the architecture, and it is giving you an indication of the coupling of the architecture. So 18 by 17 is going to be 1.06, and that is the metric. We are going to talk about DSQI. This is a Design Structure Quality Index. So this the value will range from 0 to 1. Now what is this DSQI? This is about architectural design matrix. This is about design. This is about architecture. So this is a proper matrix which will give us a number. So using the concept which were similar in the IEEE Standard 982.1 2005, the United States Air Force System Command, they use this information obtained from the data and the architectural design in order to derive this DSQI, Design Structure Quality Index, which varies from 0 to 1. So how do we compute it? Before that, there are certain AF Design Structure Quality Index. There will be 7 of them. S1 is the total number of modules. S2 will be number of modules dependent upon correct data sources or produces data used. S3 will be modules which are dependent upon the prior processing. So S4 will be the total number of database items, and S5 will be the total number of unique database items. S6 will be the number of database segments, like the record. If you make a table, one table in a database, number of records and individual objects. S7 will be those number of modules with single entry and exit. So this S1 till S7 will give numbers, and then we will compute the DSQI. How do we compute it? Before that, we have to compute D1 to D6. What is this D1 to D6? So D1 is the program structure. How do you define it? As I said, D1 to D6. This D1 is if the architectural design was developed using certain distinct method. If you have applied, or the software or the program or the architectural design was made using certain special distinct method, like the data flow oriented design or the object oriented design, then D1 will be 1. Otherwise, we'll put D1 as 0. So this is a specific value. It can be 0 and 1. This is the D1. As I said, we have to go from D1 to D6. What is D2? 1 minus S2 by S1. I told you all S1 till S7 you have to give numbers. So 1 minus S2 by S1 is module independence. Then modules not dependent on prior processing. So D3 equals 1 minus S3 by S1. So basically probability it is going. It's all probability things. So S3 by S1. Then the database size S5 by S4. You compute it and then subtract it from 1. You get the database size. Then the database compartmentalization, modularization, D5. So S6 by S4 and subtract it from 1. Module entrance or exit characteristic. This is S7 by S1 compute, subtract it from 1. So D1 till D6, this is how we get. So we have to give numbers to S1 to S7. These D1 to D6 can be easily computed. And DSQI will be simply WD. I is the subscript. That is, you have to do W1 D1, W2 D2 like this. Now you'll ask, what is W? W is simply the weight given to all these D's. This is a relative way. If you say that something is important, you say module interdependence is very important. So you will give a weight. Database size is important, you will get a weight. If module entrance exit is not very important, you will get a lesser weight. So this sigma Wi should be 1. Okay. Now this weight you have to be along, it should add to 1. If all these DIs are equal weighing, then you will get this Wi will be 0.167. So the value of DSQI what you got will be compared to the past design. So if the DSQI value is lower than the average what you have got earlier, it indicates that you need to work on your review and design work. Matrix for object-oriented design. Now, object-oriented design has a lot of concepts. We start with the creation of class, then we create objects, then we have functions inside and attributes which are encapsulated. Then we have these messages, passing through classes. Then there is inheritance going on. There is polymorphism. So Whitmire, he describes 9 very distinct and measurable characteristics of an object-oriented design. So size is a static count of these object-oriented entities like the classes or the operation or the inheritance tree, depth of the inherent tree combined with this, the size. So what I'm trying to suggest here is that there are certain distinct characteristics, and those characteristics can be an idea of matrix for the object-oriented design what Whitmire has suggested. For example, complexity. Complexity is all about how classes of an object-oriented design, they are interrelated to one another. So we'll talk about the interrelation here. Coupling is the we measure it by counting physical connections between elements of the object-oriented design. For example, the number of collaboration between classes or the number of messages being passed between objects. Sufficiency is the degree to which an abstraction possesses the feature required by this abstraction or a class. This is one more characteristic. Completeness. It will determine whether a class fully delivers the set of property for which it was being designed or written. This is completeness. Cohesion is whether all operations work together to achieve a single like-minded, well-defined purpose. This is cohesion. Then primitiveness. This is the degree to which an operation is atomic. What does it mean, atomic? That is, the operation cannot be constructed out of a sequence of other operations contained within a class. So, if certain operations are there, this operation cannot be completed, cannot be concluded until those operations are also being taken care or included. This is the primitiveness. So, if you have a sequence, that sequence will be followed. That is what we mean, the operation has to be atomic. Similarity means this will determine the degree to which two or more classes are similar in terms of their structure, function, behavior, and purpose. This is similarity. Volatility. Volatility, it measures the likelihood that a change or a modification will occur. So all these are measurable characteristics, and the product matrix for the object-oriented system can be applied to the requirement model also. So these are certain ways to understand the object-oriented design. The CK matrix suite, and this is class-oriented matrix. In an object-oriented design, the class is the fundamental unit of an object-oriented system. Because when we make a class, then we'll make objects. A class is encapsulating or containing what? Data or attribute. And then we have function. The function are going to manipulate this data or work on this data. This can be operation, this can be function, this can be procedure. So a class will encapsulate these. There can be a parent class from where the subclasses can be inherited. So inheritance means taking the attributes and operation as it is. So there can be another class which can be a subclass of a superclass or the parent. And these all collaborate with one another. So these characteristics, this can be used as the basis for measurement and matrix. So Chidambar and Kammerer, they have proposed a CK. C is coming from Chidambar and K is coming from Kammerer. They have proposed CK object-oriented software matrix suite. So we'll see 6 class-based design matrix for object-oriented systems. We'll see one by one what they are saying, because there are 6 different in this suite. Weighted methods per class, WMC. Now what does it mean? Just assume that we have a class C and we have, say, n methods in this class. And this n methods have complexity C1, C2 till Cn. So a class we have defined have certain functions, and each of them have corresponding this complexity. Now this complexity can be any complexity. For example, you assume it to be cyclomatic complexity. You know how to compute cyclomatic complexity. Basis path testing, I told you, the independent path we find out. E minus n plus 2 and number of regions and the predicate nodes plus 1. So cyclomatic complexity, you can also use Halstead's complexity matrix. But you need to normalize so that the nominal complexity for a method takes on a value of 1.0. So you just have to add these complexities. Just add the complexity. This is the weighted methods per class. So the number of methods and their complexity, these are the indicators of the amount of effort required to implement and test a class. So this is a clear indicator, WMC, that how much effort you are going to put and how much effort in testing also. If you have large number of methods, more complex is the inheritance tree, because all the subclasses are going to inherit the method of their parents. This can happen. More method, if they are very application specific, software specific, work specific, you may not be able to use or reuse it again. So limiting the potential reuse. Therefore, WMC should be kept as low as possible, as low as reasonable. In CK suite, we have depth of inheritance tree, DIT. So inheritance is a class properties are inherited by another class. For example, you have the attributes and function of class A, class B you have defined, class C you have defined, and you have inherited the classes which are above it. So one is called parent, the other is called children, like that. But the depth of inheritance tree is how far you are going to down the level. So this metric is the maximum length from node to the root of the tree. How many nodes you are covering? For example, 1, 2, 3, 4. Okay. Just compute the number of nodes. You have 4 nodes here. So this is the depth of inheritance. And since we have these C1, for example, C2, just take. The DIT of class hierarchy in this figure, as I am suggesting, it is 4. And when this depth of inheritance increase and when it decreases, that directly represent the complexity of object-oriented design. As DIT will grow, the lower level classes are bound to inherit many methods from C, C2, C21, C211 will inherit. Okay. Now DIT I am showing because here you see the bottom is quite heavy. DIT2, the balance tree, if you see here. So we want the balance kind of tree, because we want that the inheritance should be up to a limit, should be controllable. So the depth of inheritance tree, DIT, should not be higher than what we are expecting. So difficulty we will have in order to predict the behavior of the class which are in the lower depth in the inheritance tree. So a deep class hierarchy, clearly you see it means that the design complexity of your design is quite higher. Large DIT values, it implies many methods can be reused, because the C method has been reused to C2, C2 has been reused to C21, C21 is reused to C211. So reuse can be a thing here. Next thing comes is number of children. Number of children is the subclasses immediately subordinate to a class. These are termed its children, and this is the number of children. For example, here you have, this is a C2 class. Now it has subordinate, immediate subordinate classes as C21, C22 and C23. So how many number of children it has? 3. As the number of children will grow, of course the reuse will increase. But as the number of children will increase, and if you have an abstract class, if a parent class is abstract class, the abstraction of, say, phenomena will be diluted if some of the children are not appropriate members of the parent class. So these are we need a proper balance of this number of children, because though reuse is increasing, but the appropriate implementation should be there. As the number of children will increase, the amount of testing will also increase. Coupling between object classes. This is CBO. This is CK suite, one more metric. CBO, coupling between object classes. Now when you make a class, when we make the, or say the components, subcomponents on the modules, they are going to somewhat couple. So the CRC model may be used to determine the coupling between object classes, and this you can take from CRC index card. So CBO is number of collaboration which are listed in the class as is in CRC index cards. You see here, this is the collaborators, these are the collaborating classes. So all this we can get it from CRC index card. As this CBO will increase, the reusability of class will decrease. High value of CBO means what? Because there is so many collaborating classes and coupling is there, so modification will be complicated and testing will be. The CBO values for each class should be kept as low as possible, as low as reasonable. Either you take the conventional or any, coupling has to be as low as possible. CBO is coupling between object classes. If you see here example also, I tried to show you how many CBOs this A, B, C, D have. Response for a class, RFC. Now RFC is what? First of all, let us understand. Methods that can potentially be executed in response to a message received by an object of that class. Now you are receiving a message and say M1 is an object of this class. Now the invocation of R1 has happened. That is, RFC measures the immediate surrounding of a class. If some message is coming and some other, say, object are being invoked or some other thing are invoked, this is the response for a class. So we say it in the size of the response set, we take the union of the which is in getting message and what are invoked. So RFC is the number of method in this response set. So as this RFC will increase, the effort of testing also will increase because the test sequence will grow, because some input is coming here, other is getting invoked or called. So as the RFC will increase, the overall design complexity of the class will also bound to be increased, like R1, R4, R3, they will also get invoked. Lack of cohesion in methods, LCOM. Now LCOM measures the dissimilarity of method in a class by instance variables or attributes. There are different variants. Let me take an example of a class. Now we want that cohesion should be there inside a class. Now each method in a class are bound to access one or more attributes. These are called instance variable. So when the method is making use or manipulating or accessing one or more attributes, LCOM is actually defined, which is the number of methods that access one or more of the same attribute. Please understand, number of methods that are accessing one or more of the same attribute. For example, here variable ABCD is given. The method 1 is accessing A and C. The method 2 is accessing B. The method 3 is accessing A, B and D. This is I am talking about. Number of methods that access one or more of the same attribute, LCOM. So normally we talk about cohesion, but here we are talking about lack of cohesion. If no method access the same attribute, you are bound to have LCOM value as 0. No one is accessing the same one. In order to illustrate, to understand the case where LCOM not equals 0, you just consider 6 methods. 4 of the method access one or more attributes in common. So what do we say? We say LCOM is equal to 4. The lack of cohesion in methods is 4. So this is how the LCOM works. If LCOM is high, the complexity of the class design is higher. class-oriented matrix, the mood matrix suite. And this we are going to see in the next discussion. Till then, thank you so much. Take care of yourself.